Here's an example of a stoichiometry problem in which we're going to find percent yield in the end. At this time, I recommend you pause the video. That way you can read the question, understand what's being given, what it's asking you to find. You'll also notice that over here in the upper right-hand corner, I have the molar masses of potassium carbonate and the molar mass of water. That way, once I go through my stoichiometry, I'm not taking as much of your time, and it's a faster video. So the very first part says balance the following equation. If you went through it, you'll notice it was already balanced, which is nice. It isn't always. And I'm going to go ahead and do part A in red. It wants me to find the theoretical yield in grams of H2O. Anytime you find theoretical yield, that's going to be using Stoich. So I'm having a hard time writing, forgive me, but that's stoichiometry. And you're going to be given 34.5 grams of potassium carbonate. If that's what's given, that's what we're going to start off with. So 34.5 grams. I want you to notice how I'm making sure I label everything. Labeling is important. If I have grams of potassium carbonate on top, I must have grams of potassium carbonate on the bottom. And I'm going to get that from my periodic table. So that's what I calculated before the video, just to make it go by faster. 2 potassiums plus 1 carbon plus 3 oxygens, we get 138.18. And remember, every time you pull a number from the periodic table, it's always going to be with 1 mole of that substance. And forgive me, my pen's not quite working and cooperating tonight, so it's a little bit sloppy. But anytime you have a conversion factor, anytime you pull grams from the periodic table, it'll always be to 1 mole. So if 1 mole of K2CO3 is on top, moles of K2CO3 must be on the bottom. And where do we get this number from? Well, we're going to get it from our equation, and we're going to look at our coefficient. And in this case, our coefficient is 1. Anytime you use that equation or the coefficients in that equation, that's going to be your mole ratio. So we're going to go from moles of K2CO3, or potassium carbonate, to moles of H2O, because it's asking us to find H2O. Eventually we're going to find grams, but you have to go to moles first before you can go to grams. And if you look at the coefficient, that is also 1. I'm going to have to bring it down below for the next conversion. If moles of H2O is on the top, I must have moles of H2O on the bottom. And I'm going to put 1 mole of H2O because I'm going to get that number from the periodic table, and that's what I calculated above already. So notice how from the periodic table it's grams per mole. In our conversion factor, it is also grams per mole. This one is written upside down only because that's what you have to do in order to cancel out the grams on top here. So determine the order that you put it in based on the previous fraction. So if grams is on top, your grams has to be on the bottom. If your moles is on top, then your moles has to be on the bottom of the next fraction. So at this point in the problem, we can go through and multiply everything all the way through, and just to conserve room, I'm going to write my final answer over here to the left. So as I'm doing these calculations, I'm multiplying all my numerators. In this case, I have really only 2 numbers. I kind of ignore the ones when we're multiplying. So 34.5 times 18.01. That gives me 621.35 if I round it. But I'm going to be dividing by the 138.18. And that gives me 4.50 grams of H2O once I round it. I actually got 4.4966. But if I round to the nearest hundredth, it would end up getting me 4.50. So I'm going to put a little subscript of T because this is important. This is the theoretical. So what this means is, in theory, if my chemical reaction works out perfectly, no problems at all, everything is perfect, there's 0 error, and I do everything just right, this is exactly how many grams of water I should be getting in my product. However, part B, and I'm going to do that in blue, says if you only get 3.4 grams of water that's produced, what is the percent yield? This amount is called the actual. So going back, this is how much I should get in theory, but this is how much is actually produced. So whenever you calculate the percent yield, it's going to be the actual over the theoretical. You're going to multiply by 100 to get your percent. Now, your actual should typically be smaller than your theoretical, because the theory behind that is when you're actually doing an experiment, the reaction occurs, but maybe not completely. The reaction isn't going to occur more than it is supposed to, only less due to errors in the lab. So we're going to have our actual on top, 3.4, our theoretical, which is 4.50, and we're going to multiply that by 100 to get the percent yield. So I'm typing that into my calculator now. And that gets me about 75.6%. So what this means is when carrying out this experiment, the reaction only went through about 75.6% of what it should have or could have. Now if you subtract this from 100, that should get you the percent error. How much were you off? So I've had students ask me, well, what's the difference between percent yield and percent error? Well, one is like looking at the glass half empty and the other is like looking at the glass half full. Percent error tells you how wrong you were, but the percent yield tells you how right you are.